I mentioned previously that there's a difference between strength and concentration. And concentration has to do with how much dissolves, whereas strength has to do with how strongly it dissociates. That is, how strongly it breaks up into its individual pieces, whether it breaks down completely, or you have a reversible reaction where it doesn't break down completely, or you have the ones that don't break down even though they do dissolve completely, things like your sugars. But concentration has to do with how much dissolves in there. And different substances have different maximum concentrations that they can have. And most of our solution concentration equations have solute over solution. And that is an important distinction. It is stuff being dissolved divided by the total. You'll notice this is not solvent. The amount of solvent that is there is different. Going back to the prior picture here, they made 250 milliliters of solution. Well, that means you can't put the solid down in here and then add in 250 milliliters. By the way, you would not use a wash bottle like that to add this much water to it. You'd pour in some distilled water first, and then what you actually do is you don't fill it all the way up to the 250 milliliter mark. And this kind of flask is called a volumetric flask, which they mentioned over here. That measures exactly a particular quantity. Now, it doesn't have to be exactly 1 liter. In fact, they're showing here a 250 milliliter volumetric flask. And so you can have other sizes of volumetric flasks, but they have a single mark on them. They're not like a beaker or graduated cylinder where you can measure a whole bunch of different things. They have a single mark on them for measuring the total volume. Well, since we want the total volume of solution again and not of solvent, we can't just add 250 milliliters of water, because we would be adding on to that the volume, and mass is not volume, but the potassium iodide takes up some space, the volume of potassium iodide. You can't either measure the volume of potassium iodide and then just add it, because when these two mix together, the things that are dissolving fill in some of the gaps in between your water molecules. Water molecules are those Mickey Mouses, though I'm just going to draw them as little V's here, but sometimes the thing that's dissolving ends up in between them, and so then the volumes are not additive, is how we describe that. And so, as I started to mention, what you do is you put a solid in there, you add some liquid, and then you stopper it. You put a plug in the top, which they show over here on the right. They're using a glass stopper there. And you dissolve it, hopefully completely. If you're trying to make a concentrate solution that is the maximum amount that can be dissolved, it's a little bit more awkward. But you dissolve it completely in there. And then, after that, then you fill it to the special mark. And what happens is, because of imperfections that are made in the manufacturing process, they actually etch this mark on unique for each flask. And so if you have a whole bunch of 250 milliliter flask, those marks might not be at the exact same location. With solutions, we always measure from the bottom of the meniscus. Meniscus is the curve that the any liquid has, especially noticeable when it's in a small, thin container. There'll be this little curve due to gravity and due to something called capillary action, which is related to the intermolecular forces, where the water is actually slightly attracted to the glass and starts to climb up the walls of the glass. Same way that you can get water to climb up a paper towel against gravity when you dip a paper towel into a puddle. And so it starts to go up, and because of that, we just have agreed we're always going to measure from the bottom of the meniscus there for that measurement, especially because the amount it crawls up in different containers is going to change. And so then you have 250 milliliters of solution, but that solution, again, is the total stuff and is not the amount of solvent. Different concentrations that do this, and as I've mentioned previously, there's lots of different ways to measure the concentration, which is like gases, and lots of different ways to measure the pressures. But we have what's called a mass percent, where we take the masses of the two. We have a volume percent, where we take the volume of the two. We have a mass volume, where we use the mass of the solute and the volume of solution. And so we're kind of mixing those prior two ways of measuring it into this one here. And then what is for chemists probably the most common one, molarity, which uses moles and volume. There are other concentration measurements. We're not going to get into those, but the other concentration measurements don't follow this format. They might be solute over solvent in those cases, or this one compared to others. It's kind of like the equivalents that we were using in the last section, but there's one called normal or normality. And then there's also something called molality, not to be confused with molarity. One way that we tell the difference is molality is always lowercase and molarity is always capitalized. And I was doing kind of the units on these up here. The percent sign is your unit. Molarity, it's a capital M. Normality, it's a capital N. And molality is a lowercase m. And I mentioned these two just in case you come across them or see them at some point. Medically, these are probably your more common ones. As I mentioned, chemically, molarity, hands down, is the most common one. Anyway, for a mass percentage, we're going to take the mass of solute, and we're going to divide it by the sum of the mass of the solute and the solvent, because that then is the mass of solution. And because of this, we can always use this as a conversion factor, because if you're given a mass percent, it doesn't matter how much stuff you have, you can always assume that that percentage is, since our maximum percentage is 100%, we can pretend that that percentage then is the 100 grams of solution on the bottom, and then whatever your mass percent that you're given is the number in the numerator. We're just going to do some practice over those here then. We have 8 grams of KCl, and we are adding that to form 50 grams of solution. And to avoid confusion, I'm going to drop the KCl solution, though that is normally how you would label it. And I will point out they've already done the addition here. That means there would have been 42 grams of water initially, but you have to pay attention to that word there, whether they're giving you a mass of solution or a mass of water there. And then that gives you the percentage that they have here already, the 16.0%, and then that is labeled with M over M, so we can define what kind of percent solution we are looking at, where we have the 3 different percentages there. This one here, then, we're asked to do it on our own, and so then we have 15.0 grams of Na2CO3, and this time they're giving us the mass of water that's added. They are not giving us the total solution, so we're going to have to add those two. You'll see they picked nice numbers for us, so that we can just add those two pretty simply, hopefully, in your head. But you're, of course, always allowed a calculator. But 215 grams there. And so now we just do 15 divided by 250, and we get 6.00%. And again, we have to have M over M, and then we label it with the chemical label, Na2CO3. You could say solution, you could say aqueous. It's okay to, as they did here, to leave that off. I personally don't like to. But of course, that makes the answer here C. Volume, it's the same basic setup. of milliliters, and again, we can use that as a conversion factor. I'm not going to take the time to read through all of that. Mass volume, it's very similar. We kind of are mixing the two. We do mass of the solute and volume of the solution. And again, we can use it as a conversion factor. So again, I'm not going to take the time to read all that to you. Here, they want us to then write conversion factors for each of these. So this one here is a mass, and so then we know that 8.50 grams of NaOH is equal to 100 grams of NaOH solution. Here on the next one is volume, so 5.75 milliliters of ethanol. I'm going to abbreviate that the kind of organic way. ETOH is equal to 100 milliliters of ETOH solution. And the solution label is the essential one. You could get away without using the chemical ones. You shouldn't, but you can. And then this last one here is the mixing of mass and percent. So we have 4.8 grams of HCl is equal to 100 milliliters of HCl solution. I'll point out on this one, here we're given both masses, we know they're both grams. Here we're given volumes, we know they're both milliliters. On this one of them is grams and one of them is milliliters. And how do you know which is which? I suppose you could always imagine that the bottom one has to be bigger so that we can be taking this number and dividing it by 100 to actually get a percent. 4.8 divided by 100 gives us 4.8%. Of course, 0.048, as we covered earlier in this course, would be your actual numerical answer, which then we multiply by 100 or move the decimal 2 places to turn into a percentage. So I suppose you could always remember that. The volume's always 100 is another way you could remember it, or in reality, the piece that's being dissolved is the numerator, and the dissolved final thing is your denominator. Lastly, then we have the one that's probably the weirdest, which is molarity, which is going to frequently, if you're given a mass, recall from earlier in the course, I've mentioned that anytime you have grams, you should get it into moles. And so you're going to have to go back to those old calculations, unless you're just given the moles to begin with, which won't always happen. That will give you your moles, which you can then plug into this equation here and divide it by liters. And it doesn't have to be just NaCl here. 1 molar, that capital M, recall, is molar, is 1 mole over 1 liter. And so then once again we have another conversion factor, and it doesn't have to be a 1 molar solution. It could be a 0.5 molar solution, and when it's then it becomes 0.5 moles over liters. I'll be honest, anytime I'm doing a stoichiometry dimensional analysis type calculation with something like 1.0 molar, I immediately change that into moles per liter. And yes, normally we abbreviate moles with a lowercase m, but I can follow what I mean when I have a capital M, moles, based off of molarity. This is also a weird situation because normally when we do a calculation, we will start with a single number that does not have a denominator. And earlier in the year, I told you if you wanted to set it up so that all of them look like ratios, you could imagine it to be over an invisible 1. Well, now we have an actual 1 there, and so then our next step is up to us. We could do a calculation that gets rid of the moles down here if we need to, or we could do a calculation instead, work on canceling out liters here. And when we're doing stoichiometry type of calculations, frequently we'll need to do each of those. Also, a lot of times you'll be given a problem that will have 2 numbers to begin with. You'll be given a concentration. Let's say you have 3 liters of a 1 molar solution. Well, that 3 doesn't go there. That 3 is another starting number that you have. And so you can start with either number, and this is what I absolutely love about dimensional analysis and doing this thing where we cancel out our units, is it always works out if you're careful and make sure that you're using actual ratios for each of your fractions here, and you're keeping track of your units and make sure that your units cancel out properly. Now, that is all sorts of extra kind of preview information for how we're going to use this later. For just calculating the molarity of a solution, it is just this formula, same as that one there, of course. But like I mentioned, it's a little bit of a odd situation where you're given an initial value that already has units numerator denominator, although we did see that briefly previously, at least with density, where we had 2 units and we had to take care of canceling both out. Also, frequently you're going to be given volume in milliliters, so recall 1,000 milliliters is equal to 1 liter. You're going to need to know that ratio also. Anyway, practice calculation over this. What is the molarity of a 0.5 liter solution that contains 6 grams of NaOH? Well, anytime we have grams, we should get that into moles. And sodium has a mass of 23, oxygen a mass of 16, hydrogen a mass of 1, if we rounded to the nearest whole number at least, which gives us 40 grams of NaOH. And that is 1 mole. And then that will give us our moles. We could stop right there, get a numerical answer, and it's 0.150 moles of NaOH, and then plug that into the equation from the prior one that says molarity is equal to moles over liters, and so then we have 0.150 moles of NaOH over 0.5 liters of NaOH, and then that gives us 0.300 with our sig figs molar NaOH solution. By the way, solution is sometimes abbreviated as SOLN. And another way that you will see concentrations written sometimes is with a square bracket. This tends to be used later on for certain concentration calculations, like in the next topic, which is acid-base reactions. We don't tend to drop the units otherwise, but the square brackets are sometimes used, and I should mention that here. Of course, you know that with dimensional analysis, we can frequently do all of this in one step, and so I'll show that here as well. We start with 6 grams of NaOH. We're going to turn grams into moles. I'm going to go ahead and take advantage of the fact that we've calculated this one out. It'll also save me some space. 40 grams of NaOH under 1 mole of NaOH. Well, since I want moles over liters, I've already got moles in the numerator. And so then I just have to divide this by our 0.5 liters. Well, that's really just a number I'm given the problem, and I don't have to worry about having a number in the numerator denominator, and so I'm just going to put a invisible 1 there, and notice that's the same thing as dividing our answer by that there, and it's all set up in one equation, and still gives you the 0.300 molar NaOH solution. Either one works as a method to solve it out. You can go with whichever you're more comfortable with. This one here, we're given a mass, a volume, and we want to solve for molarity again, just like the last problem. So it's going to be 34.8 grams of KNO3 that we start out with. Anytime we have grams, we should go to moles, and so that's 39.1 for potassium, 14.01 for the nitrogen, and 16 times 3 for the oxygen, which is going to give us a total of 101.11 grams of KNO3 under 1 mole of KNO3. And then we're going to divide by our volume. I'm doing this like I did on green on the last slide, all in one step here. Again, if you prefer to take it in 2 steps, you can, and that gives us 1.53 molar KNO3 solution, which is choice B up here. And they've already mentioned this, that we can use them as conversion factors. Of course, as such, they ask us to write this out as conversion factors. And so here we go with that. Personally, like I've said before, I don't like to think of them as conversion factors. I just take these two here and I set whichever one on top or bottom based off of what I do. Here is a summary of these using specific solution examples. I'm going to move right along, but I'd encourage you to take a moment to pause and look at that. And then here we're solving for grams this time, being given the concentration. The formula of mass percent or concentration is equal to mass of solute over mass of solution, and then plugging in the values we're given. 14.0% of NaOH solution is equal to, let's see here, this one is 75 grams of solution, so this is the solution on the bottom on the denominator, so 75.0 grams solution, and then we're asked to solve for the mass of solute. Mass of NaOH is question mark. So at this point we multiply both sides by 75 grams. And to be clear, that's a multiply dot, not a decimal. And we end up with 10.5 grams NaOH for our answer. And this is the way that I was taught to use the formula. I'll be honest, using the conversion factor is a little bit nicer, and this is one place where I kind of like the way that your textbook did it. We have the 14%, which means we have 14 grams of the NaOH, and that is equal to 100 grams of solution, and so then we can use that as our conversion factor. So working it out that dimensional analysis way, we have 75 grams of NaOH solution, and that's essential here since we're solving for a mass of NaOH. We don't want to confuse mass of NaOH with mass of solution. I actually made that mistake just a moment ago, and that's why everything here on the slide is erased. And then we have that conversion factor that we had just a moment ago of 100 grams of solution is equal to 14 grams of NaOH. We still end up with 75 times 14. The difference here is because it's not a 14%. We're dividing by 100. Grams of solution cancel the grams of solution. We're left with grams of NaOH, and we get the same answer, 10.5 grams of NaOH. This one here is similar. We're given a concentration of the solution. We're given this time, though, the volume not of the solution but of the substance here. Well, we once again have the conversion factor then, that 5.75 milliliters of ethanol is equal to 100 milliliters of solution, and this time we're wanting to solve for the how many milliliters of solution, so we want to solve for volume of the solution. So starting with 2.25 milliliters of ethanol, so we're going to put the milliliters of ethanol in the denominator this time and the milliliters of solution in the numerator, because again we want to cancel out our units. And when we do that, we get 39.1 milliliters of solution is the maximum amount we could make, which is answer C here. This one here, we want to solve for mass of AlCl3, and we want to prepare 125 milliliters. That's our volume of solution. And here we are given a concentration of solution. So I'm going to start with the 125 milliliters, Because molarity is moles per liter, I'm actually going to need to get rid of my milliliters first and get that into 1 liter there. So milliliters cancels with milliliters. I then have the molarity with 1 liter on the bottom and 0.15 molar on top. So now my liters cancel out. I then can get rid of my molar was really moles per liter. I'd already done the liters, so moles there. And I need to get rid of my moles of AlCl3 here and turn that into grams of AlCl3 here. And I didn't quite give myself enough room up there, so I am going to work out the mass of AlCl3 here. It's 26.98 grams for the aluminum and 35.45 times 3 grams for the Cl here, and that gives me 133.33 grams, which is what I'm going to put in here. And now let's just punch it into a calculator, and when we do that, we find out that we need 2.50 grams of AlCl3, which makes it that one. Before we wrap up here, I apologize for the sound quality on this one. I've had several interruptions. We've got the door open with some noise in the hall, which was necessary here, and my window's open and they're mowing out there, and it is unfortunately necessary for me to have the window open there, so I apologize for all the background noise, but that finishes up section 4.